Hello class, this is CSE 4410, sections 1 and 2, game programming, spring 2025. Alright, we're gonna begin with setting up Unity Hub for the first time. I clearly have it installed already, but it is an updated version, so let's begin with downloading the updated version. That, as of recording this, that is version 3.11, so let's go to the page for that right now. So I'll just type in Unity Hub into search here. Start your creative projects and download the Unity Hub. That is what we need. So it's unity.com/download. Click the big download button here. Now I had already downloaded this a few times already, so it's just showing up as Unity Hub Setup 2. So I'm just gonna save that, and depending on your browser, it might ask you what to save it as, or it might just go straight to downloading it right away. Once that download is complete, open up your downloads folder to find the installer here. Double click that. User account control. Do you want to allow this app to make changes? Yes, we do. So agree to the terms of service. I'll read through this and yeah. Choose an install location. Now, I'm going to end it off here because I know every time I try to record myself installing something, the recording breaks. So I'm just gonna stop the recording here and I'll come back after it has finished installing. Okay? Alright. By the way, if you do have a Unity Hub installed and you just want to update it, just make sure it's closed before you continue. Okay? Alright. And just like that, Unity Hub has finished installing. We're just gonna run it right after we click finish. And now we wait. You need an active license to use Unity. By agreeing to the terms below, you confirm that you're eligible for the personal license. Refer to the terms for more details. Also, if you're part of an organization that uses Unity Pro, you are ineligible to use Unity Personal. Just agree to that under the assumption that you are going to agree to that anyway. There is a student license as well, so I don't know, look into the process for applying for the student license, but otherwise use the personal license unless there is a income threshold that once exceeded you must pay for the paid license instead. But assuming you have that figured out, we're gonna proceed with, oh, by the way, you must have a Unity ID in order to, well, work with this. So if you have not signed up for a Unity ID yet, do that now. Log in, and there's a login interface in the Unity Hub that isn't showing because I'm already logged in. But once that is done, we are ready to create a new project. Okay, I lied. We actually need to install a version of the Unity Hub. So if we click installs, we can see all of this. These are various different, okay, hold on. Okay, my bad. These are different installations of Unity, versions of Unity that I already had. If you want to install a different editor, click install edit up here, and I would recommend picking out a version of Unity that has long-term support, such as, well, anything with the tag LTS. You can just select one of those and install that. One of the most, well, actually, the most current version right now is Unity 6, so version 6000.0.35F1, as it's showing here. Just pick something, just pick a version of Unity that has long-term support. If you want to follow along with my tutorials exactly, That version is 2021.3.11f1. You may need to find an archived version of that to install, and then install it manually. Okay, there is a X.1 beta, but we just want something that's stable for our purposes of making games. So pick out one of these, or pick out a version of Unity that has long-term support. If you want to follow along, once again, it's 2021.3.11f1. That is the version that I am using. When you install the Unity editor, keep in mind that it is a large file that is like 5 or 6 gigabytes in size, so it may take some time depending on your internet connection. I attempted to do this in class, in person earlier last week, and the download times took upwards to like an hour. So just something to keep in mind if you are on a limited connection. The editor may take some time because it is a big file after all. Oh, when it installs, past versions of Unity came with its own editor. I am doubtful that's the case anymore. You might just have Visual Studio installed alongside Unity with a plugin for Visual Studio for IntelliSense for Unity. I'll explain what that is all about once we start writing scripts though. So when you install Unity Hub, it might also install Visual Studio. If you prefer a different IDE for your code writing purposes, there is a way to change that. We'll get to that in a little bit. For this first project, however, we aren't writing any code just yet. So let's begin with creating a new project. So I'm going to click New Project here. We want a 3D project. So 3D built-in render pipeline. Let's go with that one. Select a suitable location for your Unity project. So 3D built-in render pipeline. Give your project an appropriate name. Let's call this let's call it first-person shooter, but I already have a project with the name, so you can name it first-person shooter. I have to give mine a slightly different name. There we go. No, there we go. First-person shooter, spring 2025. Click Create Project. Oh, Windows Defender Firewall has blocked some of this app. You're gonna have to allow access. Yeah, you may have to allow access for that. So, it's going to set up a whole new project. It's not one file, it's an entire working folder. So, we're gonna let this set up, and I'll come back later, and we're gonna look into what the interface is in a bit. Okay, so now we have our entire scene working. Well, we have the entire scene set up. So, by default, the scene here will have the following things. We're gonna have a single light source. It's a directional light. It's a type of light. There are different types of lights. We'll be getting to that probably in Chapter 3. There's also the camera. That is what this is here. So, the camera looks into the scene, and what it sees is what you see in-game. There's currently nothing in here. By default, your Unity window will look something like this. We'll have a hierarchy, we'll have a project view here, we have a console view here, and on the right we're gonna have what's called the inspector. The inspector is a very important thing, by the way. So get used to the inspector. It's probably gonna be your best friend here. we also have an asset store tab here, but that's long since been deprecated, so we can just close that for now. Okay. Now I do have a set of PowerPoint slides for this, and it does outline what we're going to be doing. This is all based off of Chapter 2. I'm going to cut Chapter 2 into roughly 2 parts where we start setting up the scene, and then we're going to write a few rudimentary scripts. So, what are we going to make? We're going to make a scene that's appropriate for a first-person shooter. We are going to put down a floor, add some walls, we're going to place down some lights. Oh, I said I was going to get into lights in Chapter 3. Apparently that was wrong. We're actually going to put a few lights in this scene right now. So we're going to set up the room, we're going to create a floor and some walls, we're going to place down some lights and the camera. The camera that comes with the project already, we are going to attach that to another game object that is going to represent our player. So, this is going to be a first-person shooter. There are some extra rules that we might not get into just yet for a third-person shooter. And of course, we're going to be writing some movement scripts. These are some scripts that will be used to move the player around the scene. So, let's go back to math class and remind ourselves of what 3D coordinate space is. So, 3D Cartesian space, typically when we have 2D coordinates, we use the x and y, we use xy coordinates to represent points on a 2D plane. But this is a 3D game, so we need 3 axes and therefore 3 values to describe the location of things in space. X, y, and z coordinates. In math class, you may have learned about the z-axis as representing height, but in some cases it's the y-axis that's representing height. So a little bit of nuance regarding 3D coordinate space. The directions for negative and positive directions are technically arbitrary, but most 3D graphics tools fall under one of 2 conventions. We have either right-handed coordinates or left-handed coordinates. So, if you imagine your thumb as, think about the direction your thumb is pointing as the positive direction of the x-axis. Then your pointer finger for the y-axis and your middle finger for the z-axis. These are right-handed coordinates. Unity does not use this, but some other 3D modeling software does. Unity uses left-handed coordinates where the x and z axis are the floor and the y-axis is height. That's just something to keep in mind if you are to use another 3D modeling program in conjunction with Unity. I believe in Blender the default is right-handed coordinates, so the xy plane is the floor and z is height. But in Unity, as I said, it's the xz plane that's the floor and y is height. It's just something to keep in mind, but because of at this point, there is a lot of compatibility between Blender and Unity, so even if the coordinates are mismatched, if you were to import a Blender model into Unity, it'll just adjust it to Unity's coordinate system. So yeah, we really don't have to worry about the coordinates apart from which coordinate is height. And in Unity, the y-axis is height. We're going to create a project. We already did that. So let's begin with creating a scene that doesn't look too dissimilar from this. We're going to start with placing a few walls. So I'm going to click in this empty space here. We're going to create a 3D object, a cube. Right now it's placed at the origin, so check this out. I have this cube highlighted. Well, if nothing's highlighted, it's not gonna... Well, I should probably say it like this. If I click on the cube, it's gonna highlight with an orange border. and then it's going to have these handles that I can use to move the cube along. By convention, the red axis is the x-axis, the green axis is the y-axis, and the blue axis is the z-axis. So I can move this object along the x, y, and z directions, but I can also move it along certain planes. So this is the plane that the x-axis is perpendicular to. That's the red one here. The green one is the plane that the y-axis is perpendicular to, and the blue here is the plane that the z-axis is perpendicular to. We can also just move the cube by changing the position values in the inspector. So if, look here under transform, the transform basically says, what is this cube's position, rotation, and scale? Now, I may have jumped the gun here because we actually need a floor first. So we are gonna create another 3D object. We're gonna select a plane. It's just gonna create a big flat square. That is way too small for our purposes. So if I press S, I'm sorry, wait a second. It isn't S. If you look up here, there are some scale tools. Let's select this fourth one from the top called the scale tool. If I select that, I can scale the plane along the X and the Z and X directions. It doesn't do anything if I scale along the Y direction because, well, this is perfectly flat, so if we scale something that's perfectly flat, it's not gonna increase the height. Let's rename this plane, not SS, but rather floor. So I'm gonna right-click this, rename floor. So this is gonna be our floor. Let's resize it to something that's pretty large. You see these grid lines in the Unity world here? Technically speaking, Unity doesn't have any units, but it's a common convention to treat these units here. So this one little square here, that is by convention 1 meter square. So we want a fairly large area in which we can put our game objects. So maybe we need to scale this up by a lot. Oh, by the way, you can, when you scale this, you have the option to link the scale values or keep them unlinked, so you can scale one value at a time. Once again, scaling along the y-axis doesn't do anything for this plane here, but I want something that's fairly large, so maybe a 60 by 60 area. Once again, these little squares are by what 1 meter by 1 meter. So I want something fairly large. Just make something that's fairly large for your project. What we can do is, well, scale it up as needed. So let's just, there we go. And then we'll scale it up along the z-axis here, and there we go. So now we have a fairly large area. And now let's work on that cube. Okay, so I move the cube a little out of the way, but I can 0, 0, 0, have that be the position. Note that even though the floor is at position 0, 0, 0, and the cube is at also 0, 0, 0, the center of the cube is, well, at the center of the cube. So it's protruding like half a meter into the ground. So really I need to position it 1/2 of a meter up. So that way it's resting atop the plane. What we can do now is use the scale tool to make this cube a little bit flatter and a lot wider. But maybe that's not tall enough, so I'll just stretch it even more. Let's give it a scale something like this. So 0.2 we can be more precise by just typing in values in the scale fields here. So I'll just say 0.25 for the x, 2 for the y, and 60 for z. Once again, I need to move this up further as well. And there we go. We have now a big wall. And this is to denote the barriers, I should say the borders of our game world. So, one thing to note about Unity is the game world is not infinite. For performance sake, when you are making a scene in Unity, make sure everything is within, say, 10,000 units of the origin. So if these were real-life units, you can treat these as abstract units, but if you are to interpret these as real-life units of meters, then keep everything within 10 kilometers of the origin. For our simple game, we aren't going that far. It's only about a few tens of meters out from the origin, so we are okay. Let's rename this cube into floor. So I'm going to right-click here. I can also just type in floor like that. And now we can drag this wall all the way here. So positions, let's be a bit more precise and type in a position of 1, and 1 for the y, 30 for the x. I'm gonna now, hold on, my apologies, this should not be named floor. This should be named wall. There we go. What we want to do now is we want to make 3 more copies of this wall. A simple way to do this is to press Ctrl D. This will make a duplicate of the wall. And now we can move this to position -30 on the X. There we go. Now we need 2 more copies of the same wall, so I'll just duplicate it once more, and I'm going to rotate it about the y-axis by, it doesn't matter if it's positive 90 degrees or negative 90 degrees, it'll work either way, so I'm just going to type in 90 degrees, and now I'm going to change its position so that it is here. That is position x, 0, y, 1, z, -30. And finally, I'm going to duplicate this wall once more, slide it here, and use the inspector to make sure it is at positive 30 on the z-axis. And now we have what's basically a giant tray for our entire video game. So yeah, this might be on the large side, so you might want something a bit smaller, or maybe you want something that's even larger. Doesn't matter, same principles still apply. One thing that we could do is create an empty game object. So this is an empty game object, and let's zero out the position for best results. So this is an empty game object. There is nothing attached to it. All it has is a transform component. What we're going to do is I'm going to drag all 4 of these into this game object, and I'm just going to name this walls and floor. So this game object now has the 4 walls and the floor as children. If I change this parent object's scale, it's going to affect the scale of everything inside. What this also allows us to do is quickly scale up the world if we need to scale it up even more. So look at this. I can make the walls taller if I need to. Let's put it back like that for now. But maybe we do need the walls to be a lot taller now. So yeah, just in case the walls that you made weren't quite tall enough, we can just quickly scale them up like this. So let's do that. Okay, so now we have some pretty tall walls. If you look in the game view, it looks like that. Now here's where it gets a little interesting. We can make what we want to do is to partition this space, this giant space, into a bunch of smaller rooms. So I'm going to create a brand new game object, and I'm going to put it at the center here, 0, 0, 0, and lift it off the ground a little bit. I probably want it to be a little taller, so I'll give it a height of 2. Pull it out of the ground further, or set there. I'm going to scale this down to be a bit thinner, so let's make it 0.3 on the Z scale, and let's make it pretty wide. So now we have another wall. I'm gonna change the scale. I'm gonna change back to the move tool so I can move it over here. I'm gonna make a duplicate and move it over here. These are gonna be small walls, so let's call it small wall. What we're gonna do is make duplicates of this wall, rotate them and scale them as needed, so that way we can partition this space into smaller rooms, so that way we, for our character that we're eventually gonna put in here, there's a much more interesting space for the character to wander around. So I'm just gonna continue partitioning the space. You don't have to be exact, by the way, so if the walls aren't exact, don't worry about it. Right now I'm just scaling things up and down as needed. There we go. Scale this down a little bit and drag this over here. Take this, scale it down even more, and put it here. There we go. Well, you get the idea. We are partitioning this space into smaller and smaller rooms to give our game world a bit more flavor. So I'm gonna pause it here, and I'm gonna partition this world into a maze-like area, and then we'll come back and look at the next step. Okay, got something that looks amazing. Terrible pun. Now I'm gonna create another empty game object. I'm gonna call it inner walls. I'm gonna 0 the position on this one as well, so I'll just reset it. And now I'm gonna take all of my small walls and make them a child object. I'll make them all children of the inner walls game object. So the idea is, if our walls weren't high enough, I'll just scale the parent up as needed. So, by the way, this only works if we have the parent object at position 0. That way the walls grow up instead of growing up and down. So I have it set up so the bottoms of each wall is at 0. So that way when I scale up this inner walls game object here, it scales up all the walls so that they grow up, not up and down. Want to see what happens if I didn't do that? So, if I reset the scale on this to 1, remove all of these inner walls from the game object here, and I move them, and I move these walls ever so slightly lower, like that, and then I made them children of the inner walls. Watch what happens if I scale up the inner walls game object. Yeah, they're growing up, but if you look down here, they're growing down. So that is not what I wanted. So I'm gonna undo all those changes, put back all these small walls so that the bottoms are touching the floor, and then I'm gonna make these small walls children of the inner walls object, so that when I scale up this inner walls object, all the game objects that are children of it will inherit that scale value, and we have the ability to raise and lower the walls as needed. There we go. So now we have an area. Oh yeah, I put 90-degree walls here, but there is no reason why we couldn't, for example, have, say, walls at arbitrary angles. So I'm just gonna make one real quick, just to demo. Yeah, you can have walls at whatever angles you want. Maybe like this. And I'll put it over here. There we go. So now we have a space for our walls. I'm going to turn off the sun for now. So this is the directional light that the game world came with. I'm going to turn it off for now, and you'll see everything went dark. We're going to add a few point lights to the scene. So I'm going to right-click in this space in the hierarchy, and I'm going to create a point light. So the problem with this point light is it is way off the scene. So I need to reset its transform. You see this little dot at the... If you look in the inspector at this point, for this point light, you see this thing for the transform, and there's a little dot here. If you left click that and click reset, you reset the position of that point object. So now we have a little light that we can use to light up the scene. Alright. So let's get a little into the weeds about the different types of lights there are in Unity. So if you just right click here and go to light, you'll find 4 types of lights. We're gonna work mainly with the directional light and the point light. So a point light is basically, well, a point of light. It just radiates light in all directions, and the light dissipates the further out you go. So that's why we have one bright spot of light, and it just fades away the farther we go. We can make this light a bit smaller. The point is the lights serve as, I guess they could be representative of light sources that would be in, say, a dungeon. So these could be torches, for all we know. So what we're gonna do is we're gonna duplicate this and spread a few of them across the room like this. I'm going to create another empty game object, and that's going to hold all of our lights. I'm doing this for organizational purposes. So I'm going to drag and drop all these lights into here. There we go. So remember that directional light that I turned off earlier? When we created that 3D project, that directional light was created by default. Think of the directional light as representing the sun. So the sun's so far away that any light beams come off of it and hit the earth are as good as parallel. So when they hit the ground in this scene, they all hit in the same direction. It does not matter where this directional light is either. So the only things you could really affect are the angle at which it hits the ground, the color of the light and how intense that light is. Keep in mind that if you have too many lights, it might negatively affect the performance of our scene. So that's just something to keep in mind. Oh, you can also inspect these lights in the inspector. So, for example, we have these white lights in the scene. If I select all these lights, I can edit all of them at once. I can't edit their position because it might... Yeah, for these objects, they all have different positions, so if I try to edit them all at once, they'll just go to the same location, so I'm not going to edit that. But I am going to edit their color. So these are white lights. We want something that's more dungeony, so we want something a little more towards the reddish, maybe orangish part of the color spectrum. So I don't want to use the eyedropper here, although I could, and get this grayish light here, if that somehow makes sense. What I want is a yellowish, orangish light. So I'll just drag this little knob here towards the orange and yellow, and I'll pick something out like that. So this is a warm light. Light bulbs are a little bit weird. If you go to like Home Depot and go to the light bulb section, you'll find light bulbs in different Kelvin ratings. So these are just warmness or coolness of the light. So warm light is towards yellow. Cool light is like this, towards the blue. So this would be an intense blue light, the kind you would expect in like fluorescent tube lights in the ceiling of large buildings. What we want is a warm light, much closer to candlelight. So by doing this, we achieve a good approximation of what a fire's light would look like a little candle's light. We'll save that, and there we go. You can even see it on the walls as well. So just glowing with a little faint yellowish light. I can also change the light here, so notice how it affects the color of everything. There we go. Let's go along with this warmish. Let's go along with this warm light here. That looks like that kind of looks like a sepia tone, don't you think? Anyway. Okay, now that we have our lights set up, you can add more lights if you would like to, but I'm going to proceed with the step of adding a game object that will represent the player. So let me just collapse all of this first. Now I'm going to create a new game object capsule. So this is going to be our player. The player's like way below the ground right now, so I need to reset the position for that. Actually, the wall here, it's not a good position, so I'll just nudge it over to the side like that. Okay, so now I need to lift the player out of the ground, say 1 unit off the ground. So this capsule looks like a pill. It represents a player. So we're gonna call it player. There we go. Now, this capsule has what's called a collider. However, we're not gonna be using it, so click that little dot 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 for the capsule collider and remove component. We won't be needing the collider for this for now. What we want instead is At the bottom of the inspector is this big button called Add Component. What we want is something else. We want Character Controller. Select that, and now we have a Character Controller component on our player. Now what we want to do is find that camera so we can make it a child object of the player. Here's the camera. So we want to position the camera so that it is in where we expect the character's eyes to be. Once that's done, we'll drag and drop that camera onto the player. So now the main camera is attached to the player. Wherever the player goes, the camera goes. If I take out this game, if I pull this game tab and put it on the side here, and I start dragging the player around, wherever the camera goes is wherever the player goes. Okay, so all of this was, if you've been following along in the slides, this was all Chapter 2, Sections 1 and 2. So it is at this point where it's beginning to look into the code. So by creating the capsules for the player, we have now entered Chapter 2, Section 3. We are gonna make the player, and we've made the player as a capsule. We've taken out that collider and replaced it with a character controller. We've now attached the camera to the player. And now we're gonna write one of our first scripts. So what we're gonna do now is we're gonna understand how rotation works. So if we think about a thing rotating, we just think of a thing rotating at a fixed speed. But in Unity, we gotta think about moving the object a little bit at a time for each frame that is rendered for the scene. So we're gonna write a little bit of code to demonstrate that. So let's go all the way down here to the assets. Let's make a brand new folder that contains our scripts. So scripts, open that, create a brand new script, C# script. Let's call it spin. So we're gonna make an object spin so we can demonstrate how a spinning object would work. Okay. Let's double click this so we can open this in Visual Studio. Oh, by the way, if you want to use a different code editor, go to Edit, Preferences. External script editor will probably be by default some version of Visual Studio. You can change that to be whatever you like instead. I'm gonna use Visual Studio because that's just what I use. So double click this script that we called spin. That will open the file in Visual Studio. When you write a new script, by default it will include what are called the start method and the update method. C# does not call these functions. They're called methods instead. C# has different names for everything. One other thing is this. Any script that we make in a Unity project will, by default, inherit from a special class called MonoBehavior. So a lot of our scripts will be inheriting from MonoBehavior. That's just how it works. This is how we're able to attach scripts to game objects. Okay, so here's what we're gonna demo. We're going to add a public variable. So this is what is called, we call this a public variable, but really it's called a public field in C#. So public float speed, and we're gonna assign a value of 3.0f. The f means this is a floating point, 32-point floating point value. Double would be 64 bits. Yeah. Okay, yeah. Float is 32 bits. Double is, well, twice that, so 64 bits. We put an F to denote that this is supposed to be a double. No, not a double, a float, my mistake. So now we have this speed value. So, what do these methods do? Well, they kind of say it. It says so in the comments. So, the start method is called right before the very first frame update. Update is called once every frame. So, you may have, in case you've been looking into Unity tutorials for a while, one of the things that you'll probably be aware of is to remove any and all update methods that don't do anything. The reason is simple. It's because if we just leave in unused update methods in any of our scripts, it's just gonna waste computing time that we could be using for our project. So it's a simple way to optimize your game. Make sure you don't have any extraneous update methods in any of your scripts. But we are going to be using this script. What we're going to do is we're going to make a object rotate. Oh, by the way, this is more of a code style thing. It doesn't matter if you place your curly brackets on the same line as your method declaration here, or if you put it on a new line. What's more important is that you be consistent with how you write your own code. Okay? So let's write in here transform.rotate. So this thing is going to accept three values that are the x, y, and z axis rotation. So to visualize that, imagine this is an airplane. We have, on a plane, we have pitch, roll, and yaw. So pitch, roll, and yaw correspond to the object's x, z, and y axes. These are called Euler angles. So when we pass in three values, when we pass in three values into this update method, we are going to change the rotation of this game object's pitch, roll, and yaw. We're just gonna rotate one value. That's going to be the y axis. So we're going to change the yaw. So we're just gonna type in 0, speed, and 0. There we go. So now we have an object that is going to spin. Okay, now we actually need one more game object, so I'm just gonna create another cube, put it somewhere in the origin, like that. Make sure it's not like in the way of the player. Move it over here. And I'm gonna drag and drop this spin script onto the cube here. Or you can put it also on the cube that's also in the scene. Doesn't matter either way. Or you could drag and drop it in the inspector. That also works. But now I have two of them, so I need to take out one of them. There we go. For the sake of demonstration, I'm gonna rename this to Spinny Cube. So what we need to know, the thing we need to know is this cube is going to spin by having the update method called transform.rotate every frame. So when we play this, it's spinning really fast. Spinning. Spinning really fast. Okay, that might actually be a little bit too fast, and here's the worst part. The spin rate is the rate at which it's spinning is dependent on the frame rate. Not everyone is gonna have like bonkers computer hardware where, like I do, I have this and this. Not everyone's gonna have that. So to ensure that our games are fair in cases where frame rate matters, we want to make this cube rotate at a rate that is agnostic of the frame rate itself. Because, and more to the point, this is way too fast. So, what we want to do is this. We want to impose a limit on how fast that cube rotates. So, to do that, it's a simple fix. We're going to multiply this speed value by something called Time.deltaTime. And I probably spelled that wrong. It's capital T time dot delta time, lowercase d, capital T. So now, what this does is constrain the rotation rate of our cube to something that's a lot more sane. Okay, that might still be a little bit too slow, but in the inspector we can adjust the rotation rate to what we want, but the point is this. It's now going to rotate 3 units times time.delta-time, instead of rotating 3 units per frame. And frame rate is way too variable, so the rate at which this cube was spinning previously was dependent on the frame rate, which could vary based on how much stuff there is to process in the game, and also how powerful the user's computer is. What we have done is made the cube rotate at a rate that is no longer dependent on the frame rate. But if it's still too slow to your liking, we can always just adjust the rotation rate to something absurd. Let's put it back to 3. 100. Alright, so now we have a spinning cube. We may or may not want this for testing purposes, but I'm just gonna leave this spinning cube here because when it comes to the movement of our player, we're going to apply the same methods. So, okay, there is one other thing that I need to get into. There is something called local and global coordinates. So, every game object has its own local origin. So, for example, these inner walls have a local origin that all of its children use as a reference point for where they are. Okay, so here's the thing. The entire project has an origin, and everything is some units away from the origin. Every game object has its own local origin, and if we have nested game objects like this, then this game object is 16.51 units away from the origin of this inner walls game object, no matter where it is in the game world. So if we pick out some other game object, small wall 12, this is 21.61 and 26.3 units away from the origin of the inner walls game object. Even though that is like negative 82 and 107 away from the global origin. So every game object has a set of local coordinates that, as particularly in cases like this, those local coordinates are used to determine where it is, where game objects are in relation to a parent game object. So, the point is this. The scene in which we place our game objects where they are in the scene, those are global coordinates. Local coordinates, game objects have their own local coordinates. So when we rotate a cube, we're applying that rotation on its local axes. Another thing to note about local and global coordinates, local coordinates of a game object move with respect to the global coordinates. Global coordinates never move. So what I said about the nested game objects applies here as well. The fact that all of these walls are always some distance away from this inner wall's parent game object, regardless of where that parent object is in the world. So if I put this back in the origin, then as far as these nested game objects are concerned, they haven't moved anywhere relative to the parent object here. So when we apply a rotation, when it comes to rotation, when we apply a rotation to a game object, we are applying it to that game object's local axes. Yeah, especially when it comes to rotation. So once again, local coordinates of a game object can move with respect to global coordinates. Global coordinates never move. Ignore this one. Ignore that slide. I don't do short answer questions anymore. Okay, so we're going to make a script that allows the player to look around in the scene. So we have a camera attached to the player, but we have no way of moving the player around right now. In fact, if I play this game right now, and I go here, I can't move. But that cube is moving. But I want to move. I want the player to move. Let's write a script. Let's write a new script that lets the player do that. Let's call it mouse look. Okay, so now we have a new script called mouse look. We're going to do some work on this script here. So this is section 2.4 of the slides in the book. Now, the next script we are going to write will have the player basically move around. Yeah. First, we're going to have the player move the camera around relative to the scene. And finally, we're going to have the player move in the scene. So this is really a two-step process. First, we're going to have the player look around, and then we'll have the player move around. Okay, so it's section 2.4. Now that we've created our script, but we need to attach it to the player. So I'll just drag and drop this onto the player here. Yep. Now let's edit that script. Okay, so first we're going to need a public enum. If you don't know what an enum is, it's just a way of... I'll be right back. Yeah, think of an enum as values that... These are just textual things that represent values. So, for example, level, low, medium, high. We're gonna use that to represent the different modes of movement for our mouse look script. So there are 3 modes of movement that we're going to program. Those are... Oh, we have to name this as well. So we're going to move our camera along the mouse x-axis, mouse y-axis, or both. So let's do this. Mouse x and y. We can assign values to these as well. By default, it's just going to start at 0. So there we go. Now we need a public field in which we can change the rotation mode of the mouse look script. So by default, it's going to be the first mode, mouse X and Y. We're not going to use the start method here, rather we're going to use the update method. So I'm going to write some code in here as follows. If axes equals rotation axes dot mouse X, then this is going to be horizontal rotation. Else if axes equals mouse Y, so this is going to be for vertical rotation. Else horizontal and vertical rotation. Gotta fix my light. Gotta fix my light something. So, what we have done is written the following. So, we wrote an enum that associate names with values so we can more easily identify. This is so we can identify different mouse movement modes here. We have a field in which we can specify what movement mode we are using, and then we have an update method that, based on what movement mode we have selected, it's going to move the camera based on that. Or I should say, rotate the camera. Okay. Now let's add 2 more lines of code. After the axes field, we're going to add another public mode. Sensitivity for the horizontal axis. So sensitivity HOR 9.0. We're just going to default this to 9.0 right now. And in the code block here, we're going to write in transform.rotate. No. Okay, 0 for x-axis rotation. Sensitivity horizontal times. We're going to write something special here. It is input.getAxis mouse X. We are getting horizontal movement from the mouse and multiplying that by the horizontal sensitivity. That is the Y value. Next, we're going to type in a 0 for the Z value, so no Z-axis rotation. There we go. So, let's break this down once more. Much like what we had written in that spin script earlier with the spinny cube, we are using the same method as before, but we are applying a rotation to the player. When the mouse moves, we rotate the player. But when the mouse moves, we should only rotate the player based on horizontal movement from the mouse. So the mouse is here. If I move it to side, that should rotate the player about the y-axis. So it's like here. Or at least that's how. Let's try it out. If I go here, nothing's happening. Did I even set it up right? No, I did not. I had the wrong mode selected, so I'm gonna have to change to that mode. So, mouse X. So now if I move the... There we go! We can now rotate the player around the scene. Not unlike how you have an office chair that can just spin. 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 There we go. And now I'm a little dizzy. Yeah, eventually the player will just get dizzy, but that's only one mode. That's only one mode of movement. We want another axis of rotation. Yeah, so when you try this out, make sure your axis is set to mouse X, because we haven't programmed the other two modes just yet. When we look at up and down, well, you can probably imagine where this is going now. We have horizontal movement on the player already. On the player already. Well, horizontal rotation on the player already. So we can just spin the player around and around as much as we want, but we want the player to look up and down. The problem is my neck. No, there's not a problem with my neck. It's my point is our neck has a limit on how far up and how far down we can look. So when we apply these vertical rotations, we need to apply some limits. So here's what we'll do. Let's go back to that rotation script. We're going to add a few more fields. Another sensitivity for the vertical axis, so we'll set that to 9 as well. I'm going to add 2 fields here, and they're both public fields. Those are how far up you can angle your head and how far down you can angle your head. Those are minimum vert and maximum vert. Oh yeah, and these are in degrees. Also, we need a private float that we use to keep track of what is our current rotation. So, that's gonna be set to 0 for now. Now that we have these fields set up, we can now write the code for our y-axis rotation. So, we're gonna say vertical rotation minus equals. So we're gonna decrement this private vertical rotation here by input dot get axis mouse y times the vertical sensitivity. Then we're going to clamp that value. So that way, that vertical rotation is within the minimum and maximum values that we have assigned here. So, vertical rotation equals mathf.clamp. So the first value is the value that we want to clamp. So, and then the minimum and maximum values allowed. The next line of code we're going to add is float horizontal rotation equals transform dot local Euler angles dot y. So remember when I was talking about those Euler angles? Every game object has a set of Euler angles that describes how it's rotated in space. We're just taking out one of those values. And then, because we need both this vertical rotation and the horizontal rotation, and we're gonna do this. We're then gonna say, we're not gonna use transform.rotate here, we're gonna use a different means of changing our rotation here. So that is going to be transform.local Euler angles equals. This might be a bit new to you because local Euler angles is a data structure called vector tree. It's just a data container that holds three values, x, y, and z. Or at least that's what they're usually meant to be used for. It has three values, x, y, and z, that can mean different things in different situations. In this case, they are being used to store our Euler angles. This transform.local Euler angles value here, that must be the right hand side of this must be a vector tree. So we're just gonna make a whole new vector tree, and we're just gonna pass in the three values for this vector tree. This vector tree is representing the Euler angles of our game object. So all you gotta do is just pass in vertical rotation, horizontal rotation, and 0. So yeah, there we go. So now let's try that out. So the idea behind this mode of rotation is the player can move their head up and down with limits. And that limit is the neck. So if I go to the player here, I'm gonna change the axes to mass Y. Now, if I go to the game view, I can nod my head up and down. But I cannot move my head side to side. But I can if I change the mode on the fly. But we have this weirdness going on. Yeah, we're gonna have to address this later on. Yeah. So maybe now's a good time to look at the mass X and Y movement. So right, there's also a little bit of information on Euler angles versus quaternions. A quaternion is a do you remember imaginary numbers from back in like advanced math class? Well, a quaternion is a four-dimensional analog to that, and it is used to represent 3D rotations in certain contexts. So, as the story goes, a mathematician was walking on a bridge, had the idea of, oh, it has to be a four-dimensional number, and then wrote the entire equation on the side of the bridge. And to this day, there is a plaque commemorating what was basically a piece of graffiti that is actually a very important identity in the field of quaternions. Don't worry too much about quaternions. They're just another way of expressing rotations in 3D space. It just has a few advantages over Euler angles. So yeah, don't worry about them too much for now. Just keep in mind that there are two ways to represent 3D rotation in space. The first one is Euler angles, the second one is quaternions. Quaternions require 4 values, not 3. So if you were to work with quaternions, you're probably going to be working with a vector 4, not a vector 3. So you can convert between the two, and there are libraries. The libraries in here have functions that would convert between one and the other. So for now, don't worry too much about quaternions unless we specifically need to work with a quaternion. Okay, let's reevaluate what. Let's go back and see what we're gonna do next. Okay, so for the last thing we're gonna do here, we're gonna code it so that we're gonna have horizontal and vertical rotation at the same time. But it's not as simple as copy pasting this line of code and then this line of code in here. It's a bit more involved than that. So we need to get both the horizontal and vertical rotation. So if there is some code that we can transplant from one to the other, it's probably going to be this one. So let's begin with this line of code. So vertical rotation and a clamp value. Now, we're going to take that vertical rotation and then clamp it. Then we need to calculate what's called a delta. So a delta is simply just a change in a value. Float delta equals input.getAxis mouse x times the horizontal sensitivity. And then float horizontal rotation equals transform.local Euler angles.y plus delta. And then we're going to do the same thing here where we assign our local Euler angles a brand new vector 3 that contains our vertical and horizontal rotation. And that's all we have to do. So let's recap. We wrote a single line of code that would handle horizontal rotation as though you were spinning in place. We then wrote code for vertical rotation that would represent moving your head up and down. And now we've combined those two functionalities into one mode where we get to do both. So we get to look up and down as we rotate on the spot. Right, so let's go back to the editor and change the mode here to mouse X and Y. And now we can move freely. Or at least we can move the camera freely. We still don't have player movement. So yeah. Okay, before we continue, there is one extra option we can add here. I'm just going to add it here. So I'm going to have to add back that start method. So I'm just going to type in private void start. Rigid body equals yeah, so this is an optional piece of functionality that you could add here if let me get this right. If rigid body does not equal null, yeah, so this is just extra functionality. What these few lines of code does is it makes it so that when your player moves around, it will only move around if the player types in controls. Well, let me back up. What this code does is this allows any rotation from any source that isn't the player's player controls. So if the player starts tumbling on the ground, it won't result in the camera also tumbling around. So basically the player will only rotate whenever the player uses the controls to make the player rotate. our finished mouse script should look something like this, and hopefully you should be there already. Alright, just in case, take a good look at the screen here. Hopefully this is clear enough to see on YouTube. I am recording this at a 4K resolution and downscaling to 1440p. If I need to zoom in, I can, so maybe like that. This might be nice and large and legible. There we go. So take a moment to look at your code and see if you have anything missing. Okay. Now, let's get to work on keyboard controls for moving the player around. So now what we've done is we've made controls, we've written code for having the player move the camera. Now we need controls for moving the player around. So, let's make a whole new script. We're going to call it FPS input. Wait, that's a folder. My mistake. Create a new script called FPS input. So we have a script that rotates the player based on mouse movements. So it rotates the player so that the player can look around, but we need a separate script so that the player can move around. Let's open this brand new script. First, we need a brand new field. We need a public field. And now, what we can do here is we can add a method called transform.translate 0 speed 0. So, much like the rotate method, when we do transform.rotate, it just spins, it just applies rotation to the object's Euler angles. When we do transform.translate, we are moving the player along its local axes. So, yeah, let's just try this out. If we take this script and attach it to the player, like so. I'm going too fast! And if you look in the inspector, I am going way too fast. So just like that, I am gone. So, that is a first problem. Because the update method is called once per frame, we are moving at a ludicrous speed. So, let's keep that speed under control by... We don't say 0 speed 0, we say 0 speed times time.deltaTime. So that way, instead of flying off at a ludicrous speed, we now fly off at a more reasonable speed. A speed that, once again, is agnostic of frame rate. I'm moving. Okay, but here's the other problem. I am moving up. So, yeah, I'm moving up. So, what that did was apply a transform. Basically, we are translating the player up by 3 units per unit time. 3 units times time.deltaTime. So basically, you're going up in the sky. what we want instead is X axis movement. So this is, remember, this is X, Y, Z, and Y is up. So we should probably move that out of the way. So we have this instead. So now we just play around with this in the scene. Oops, I'm going sideways. Or am I? Well, I can clearly see all the game objects here, but... Okay. Maybe that's enough playing around. Let's get to actual code here. So, let's go back to that update method and add a few more lines of code. So, float delta x equals input.get axis horizontal times speed. Float delta y equals, I'm just gonna copy this line of code and then replace the horizontal with vertical. So now instead of this line of code, we're gonna do delta x 0 delta z. Okay, so now that we've written our lines of code here, we have delta x equals input.getAxis horizontal times speed, and float delta z equals input.getAxis vertical times speed. We pass those two values, delta x and delta z, into transform.translate. So we are now moving by this much on the x-axis and this much on the z-axis. So let's try that out in the game. So now we have player movement. So if I press the arrow keys, and by default these are the arrow keys, but they are also WASD, you can probably see a problem now. We are going way too fast. I can't even see the... I have a jet fighter now. So now we have that problem we had before, where we have movement based on the frame rate. So yeah, there are a bunch of issues here. 1. The player is moving way too fast. 2. The player can move through walls. And 3. The player can fly. We don't want any of those to happen. So the first issue is simple. The fact that we are moving way too fast tells us that we should probably be multiplying by Time.deltaTime. So let's go back to our FPS input script here, and we're going to multiply these by Time.deltaTime. I'll just copy this line of code, paste it here. So now, if I play this game again, I should be moving at a much more reasonable speed. I'm no longer flying, but... Well, I'm no longer moving at ludicrous speeds, but I am still clipping through walls, and I can still fly. So that's issue number 1 fixed. The fact that we were moving way too fast. I just have to fix the others. Now we just have to fix the 2 other issues. So, for the second issue, the fact that the player can clip through walls means we need collision detection. So, earlier on, we had a capsule collider that we took out and then we swapped it for a character controller component. So, yeah, remember early on we added a character controller component to our capsule. For collision detection to work, we want to move the player using the component rather than changing the player's position. So what that means is we shouldn't be using transform.translate. We should be using something else instead. That something else is as follows. So we need a private variable that has a reference to that character controller component. So here's how we do that. We need a private field, character controller. Oh, give me a minute. Okay, so now we have a field for our character controller, but right now, if we just ran this as is, this variable is gonna have a null reference. So what we want to do is in the start method, we're going to assign that variable here, character controller. We're gonna say character controller equals get component, and in angle brackets we're gonna say character controller, and then left and right parenthesis. That way we get a reference to the character component, the character controller component that is attached to our player. So remember we had attached this character controller component here? Well, now we have a reference to that in our FPS input script. So here is where things get interesting. We were previously multiplying by time.deltaTime, but we won't be needing that anymore. So we can just comment out that line, or that portion of the line. So no more multiplying by time.deltaTime. We're just gonna multiply. We're not gonna multiply by time.deltaTime anymore. So now we have a delta x and delta z. Well, rather, we're not going to multiply by time.deltaTime here. We're going to actually do that a little bit later. So we're going to take these delta x and delta z values. We're going to do this next. We're going to create a brand new vector tree. So this is going to be a movement vector that tells us how much our character is going to move in the current frame. So movement equals new vector tree, and in parentheses I have to pass in delta x, 0, delta z. Next, we're going to make sure the player doesn't move too fast. By that I mean, so this vector is going to have a length, and we're going to make sure that length isn't too much. So what I'm gonna do next is movement equals vector tree dot clamp magnitude. The magnitude with a vector you have, it's basically a arrow with a length. The magnitude is the length. Basically what we're saying is make sure when this character moves by this vector, it doesn't move too much. We clamp the magnitude so it moves an allowed amount. So vector tree dot clamp magnitude, movement is the first argument, that is the vector itself, and speed is the second argument. That is the speed field that we have here. So we're gonna be moving no more than 3 units per frame. Well, actually that's not true, because we're actually gonna multiply this by time.deltaTime again. So previously we were multiplying this by time.deltaTime. Really the thing that's changed is the order of operations. So we would be multiplying by time.deltaTime too early here. Instead we want to change that after we have clamped the magnitude. So movement times equals time.deltaTime. And then finally, our last line of code is to replace this with character controller dot move, and we pass in that movement vector. So now for each frame, the character is going to move some amount, but the movement is applied to the character controller instead, not the character's transform. So that's really the main difference here. And the reason why we did this is so we can get collision detection working. So if we move again, I am now hitting the walls, which is exactly what I wanted. Okay, there was actually one bug that I had accidentally introduced, and you may have just seen it here, but it's the fact that I am moving forward and backward, but I'm not really moving forward and backward. I am pressing the down arrow key, but I'm moving forward instead, and that's because I am moving relative to the moving relative to the global X and Y axes, not my local X and Y axes. So yeah, there was one step that I forgot. There was one line of code that I had forgotten, and it was this line of code. Right after the multiplication by time.deltaTime, I should say movement equals transform direction. I have to transform this local movement to global movement. So transform from local coordinates to global coordinates. Okay, so let's try this again. I'm gonna play it again, and hopefully when I move, I am moving relative to the player. I am moving back, moving forward, moving left, moving right, turn, moving left, moving right, moving forward, moving back, turn again, get smacked by the cube. So it's working. Except I can still fly. So yeah, that's another issue we still have to resolve. Okay. Now that a player can collide with walls, the last thing is to fix the fact that the player can fly. Collision detection works, so now we can add gravity. So one more change is needed here. We're gonna simulate having gravity on the player, so what we've done so far is all this here. So really what's going on is this. Look really closely as to what's happening. When I rotate around with the mouse, it's actually rotating the player and not the camera. So when I look up, that is the direction in which I move, so I can fly. And I can bonk my head on the walls. So really what we've done is kind of coded this camera movement incorrectly. So really we need to separate. So to make sure we don't have the player moving in the direction in which we look, we need to decouple horizontal and vertical movement now. So bonk and bonk. Let's go fix that now. So here's what we need to do. We have this mouse look script set to mouse X and Y. What we really need to do is have a second mouse look script attached to the camera. So here are the settings we need. So for the player, we have the mouse look script that should be set to mouse X. For the camera, we should conversely set that to mouse Y. So now the two horizontal and movement. So now the two horizontal and movements are now decoupled from one another, and now the player can freely move around without flying. This actually preemptively fixes a bug in which if we did not decouple horizontal and vertical movements, and we were to look up and add gravity and have added gravity to the player would be sliding back. So this preemptively fixes a bug that's described in not only the book but also the lecture slides, which is obviously based off of the book. So now if I run into the cube, I'm colliding with the cube, it's knocking me around. What we need to do now is apply gravity to our player. So So let's apply gravity to the player. And we're gonna apply it as follows. Let's go back to that FPS input script. We're gonna create a value called gravity. We're gonna set it to, well, the gravity on Earth. So that is 9.8 meters per second squared going downwards. Let's go back to one line of code where we had written that here. So, between clamp magnitude and multiplication by time.deltaTime, we're going to do this. Movement dot y equals gravity. So now we've applied gravity to our character. I'm going to add some comments to this code to make sure we understand what's going on. So, give me a minute. Okay, so now I've added comments to outline what we are doing. We are getting the horizontal and vertical movements from, in this case, it's the player's keyboard. So, in my case, it's the arrow keys. Since WASD doesn't work on my computer, I am creating a new vector to represent this movement. I am clamping it so it moves no faster than its speed. I am applying gravity. I am multiplying by time.deltaTime to make sure it is moving at a rate that makes sense, but is also agnostic of frame rate. I am then transforming those local chords to global chords, and finally I am passing that movement vector into this move method that is from the character controller, whose reference we have gotten from calling getComponent. At the same time, we had decoupled mouse X and mouse Y movement so that the camera rotates independently of the player, but the player can still rotate freely. So that decoupling is to make sure that when we move, we do not move in the direction that we look. Because if we did, that's how we were flying. That's how we achieved flight. Or at least that's how we were achieving it previously. So, we have basically completed everything in this video on how to get character movement in this maze-like environment. This may take some time for us to complete in class, so it could be over the course of at least 2 class sessions. This video is gonna have to be spliced together because it took nearly 2 hours to record this whole thing from start to finish. That including the setup for Unity itself. So I'm gonna end the recording here, and when this is uploaded to YouTube, I am going to cut it up into chapters. So, yeah, I'm gonna have quite a bit of work to do, but hopefully this is. But the hope is that this is going to help out with explaining what we are doing here. So now we have an environment in which we have. Now that we have an environment in which we can have our game, we can later on add stuff to it. So this is all just basic, putting stuff in the scene and writing a few scripts to get things moving and rotating, right? So that's going to be the end of the recording here. I'll expect this video to be uploaded sometime during week 2. Well, probably it'll leave by week 2. But yeah, that's going to be it for this video. And then hopefully, once all is said and done, we can look into chapter 3 and making the scene a lot more interesting. Oh, let's save this scene right now. Save. Alright. Thank you, and I'll see you in the next video.